Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper from the Hugging Face trending list, published on September 29, 2025, about 5 days ago. It argues that simply valuing a uniformly random policy is enough to pick optimal actions in math reasoning, and the resulting method, ROVER, raises quality by plus 8.2 on pass at 1 and plus 16.8 on pass at 256, while increasing diversity by 17.6%. The paper is titled, Random Policy Valuation is Enough for LLM Reasoning with Verifiable Rewards, and the implications for model training are quite significant. This paper replaces complex policy optimization with a softmax over random policy Q values, stabilizing learning and preserving diverse solution paths. Alright, the introduction set the premise that random policy valuation could replace heavy policy optimization. Figure 1 presents 3 views. The left panel shows pass at 1 and pass at 256, where ROVER leads, about 23 and 72 respectively, beating DAPO, Reinforce++, GRPO, and PPO. The middle cartoon contrasts a tool-heavy approach with a lightweight ROVER that still picks good apples, which signals simpler training. The right radar chart reports higher diversity for ROVER across distinct strategies, cosine distance, and utility. Well, Figure 3 presents the core ROVER idea. The graphic shows that evaluating the uniform policy, denoted pi-u, yields Q values, and greedy action selection on those Q values, produces an optimal policy. The left surface represents Q under the uniform policy, which encodes success likelihoods because each continuation is sampled uniformly. The right stack contrasts the uniform policy box with the optimal policy box, while the slanted banner highlights the greedy selection step. So Figure 3 presented the ROVER shortcut through random policy valuation. Figure 2 shows generalized policy iteration, which alternates between evaluating a policy and improving it so the learning target keeps shifting throughout training. The left column depicts changing value landscapes for pi0, pi1, up to an optimal pi star. The right panel illustrates the loop of evaluate then improve steps marching across contours, which explains why methods like PPO can be unstable and heavy. So the previous figure showed why generalized policy iteration kept shifting targets. Table 1 summarizes how math reasoning under verifiable rewards differs from traditional control, which explains why a lighter method works. The table contrasts deterministic transitions, episodic binary rewards, and a tree-like state space against the cyclic, sometimes stochastic setups in games like Atari. It also notes longer horizons and larger action spaces, because a powerful pre-trained model explores vast branches. Alright, Table 1 contrasted why math reasoning fits a simpler setup. Algorithm 1 presents the ROVER training loop, starting from a pre-trained model and sampling prompt batches, then rolling out n responses per prompt and mean centering the rewards. The core step computes Q as rho times log probability under the current model minus log probability under the frozen old model, then forms a target by averaging next token Q over the vocabulary with a stop gradient. The loss matches predicted and target Q with a squared error, and an atom W update adjusts the parameters. Algorithm 1 laid out the training loop and its stable Q targets. Figure 9 compares pass at K on Q138B base, and the red ROVER curve stays ahead, while the gap widens as K grows, because exploration remains diverse. Panel A shows steady gains on AIME 2024, surpassing baselines across all K. Panel B reports similar dominance on AIME 2025, where several baselines plateau. Panel C highlights the largest separation on HMMT 2025, with ROVER accelerating while others level off. So Figure 9 showed widening gaps at higher K. Table 2 reports pass at 1 across benchmarks, and ROVER tops every column while keeping the strongest averages. The QN34B section shows an average of about 36, beating the best baseline near 34, with sizable lifts on AIME 2024 and AIME 2025. The QN38B section rises to about 48 on average, outpacing the best baseline near 41 and nearly doubling HMMT 2025. Wrapping up, 2 takeaways stand out. Valuing a uniform random policy yields Q values that are sufficient to select near optimal actions, and ROVER turns that insight into simpler, stabler training that boosts accuracy while preserving diverse reasoning. The broader implication is leaner reinforcement learning with verifiable rewards that should transfer to other verifiable tasks. That is it for this episode of the AI Research Roundup. I am Alex. Thanks for listening.